So welcome back everybody. In the last slide we saw that if we are given a SQL query, we first consider single relation plans by considering the selection attributes on it and make an estimation of the results that will get generated from this selection condition. Next, in pass 2, what we do is we connect two single relation plans that we generated in pass 1 and make an estimation of the join between the two. So here we go one step forward. So remember that we considered one plan which is R, T, S and U. So R, T, S and U. So this is our graph of tables, and let's say that I have so I am going to consider this one plan, and remember that we had considered a bunch of other plans by chopping off this graph of tables in a systematic manner. For this particular plan, what we have done until now is we have considered the selection conditions that might be there on top of this singularly and done a cost estimation of this. From the cost estimation, we have chosen an optimal strategy for accessing each of these relations singularly without doing any joins. So until now, chosen most cost effective way for accessing each relation individually. Next, what we are going to do is that next we are going to consider the join conditions. Remember that whenever we have left deep plan tree, you have to always do a bottom up evaluation of cost estimation. So in this case, we are going to consider the join between R and T, and for that join, remember that we considered reduction factor to be n keys column 1, n keys column 2 for the join when index available. Okay, or otherwise we always consider 1/10 of the result. So now let me explain to you how we are going to do the estimation of this join after applying the selection conditions, whatever they may be, on top of, let's say, R and T. So remember that we did some result estimation over here. So this was I would say estimation 1 and estimation 2. The size of this join is estimated as estimation 1 into estimation 2 divided by the this into the reduction factor. Now how is the reduction factor decided? That depends on your join condition. So here R and T are joining on attribute 3. So they are joining on attribute 3. Now the options I am going to consider over here are: is there index on attribute 3 for R and T and or T, and then if not, file access cost. So now I am going to do, for example, I am going to do an estimation in this format. Remember that these alternatives basically and which one to choose depends on the system catalog information that is available. So I am going to pick always, when explaining with an example, I am going to always make one choice and do the further cost estimation based on that choice. So let's say that I have a index available on attribute 3 for table T. So our original query tells us that there is no selection condition on T. So estimate 2 is actually going to be equal to the T tuples that are there, total number of tuples that are there in the in this table T. So I have index on attribute 3 on T. So which means that in my 1 upon n keys column 1, n keys column 2, I have exact estimation available for n keys column 2. Let's say that estimation is 1000 keys, and I don't have index on attribute 3 for table R, but I have index on attribute 1 which did an estimation of the results. So now how I am going to do the cost estimation for this join is, so remember that I have estimate 1 from the selection applied on R into T divided by 1000, which is the n keys column 2, and I have to apply a reduction factor on this estimate 1 to make it available for the join cost estimation. So that reduction factor is going to be 10% because no index information available. So for this join, now my cost estimation is going to be the estimate 1, that is after the selection application on R, whatever the number of tuples that get generated, into the tuples that will get generated from the right hand side, which is T divided by the n keys column 2, and then on top of that I am going to apply the reduction factor 10% because I don't have the index available on attribute 3. This value I am going to store as the estimation 3 for this join. Now when I go to this column, this join, I am going to inductively apply the same process. Now I am going to assume that this is the result and its size is estimate 3. I am going to apply selection condition on top of S, which I have already done for pass 1 for a singular relation cost estimation. That I am going to consider as estimate 4, and I am going to make a estimate 5 over here by taking into consideration estimate 3 and estimate 4, and further taking into consideration any indexes that might be available on S and so on and so forth. So this as you can see, this process inductively gets applied, and at the on top I am going to have estimation 6 over here and estimation 7 over here. So estimation 7 actually gives me an estimate about the total number of results that are going to get generated by the query, the total cost of the query. So total cost of the query is summation of all estimates 1 to whatever 7 in this particular query. You would wonder that if the final number of results that are getting generated are given by estimate 7, then why do we want to consider all others? Because at every operator we have to perform CPU operations, IO operations, which are directly proportionate to the number of tuples that will get generated. So the total cost of this particular query plan is summation of all the intermediate estimations that you have generated. You do this estimate generation for every plan, and unlike what you might be thinking that if all the query plans are equivalent, aren't they going to generate the same number of tuples? Although eventually when you actually execute the query, the total number of tuples are going to be same, the estimations can change drastically depending on what indexes are available and what assumptions you make. So if you make uniform distribution assumption, then the estimate is going to be different. If you have histograms available, then the estimation is going to be different. If you make an assumption about always a value having only 10% of the data whenever doing a join or selection, then the estimation is going to be further different. So for this one particular plan, I have shown you stepwise that how basically the estimation at every level is going to be done and what is the total cost of the query. Given a query, we already saw that this query had at least 3 different plans. There can be more than them. So for every plan you do this estimation and then you pick the plan which has the least cost, and cost is associated with the cost is equal to the total number of estimates or cardinality, that is cardinality of the results that get generated. So you pick the least cost plan by doing these kind of estimations. So I will leave the exercise for so there are some exercises at the end of the chapter 14 as well, which will give you the exact number of tuples or exact number of index entries in a particular join query, and will ask you to do the cost estimation or cost estimation and picking the most cost effective plan. So we saw this, that for pass 1 you do single relation estimation, for pass 2 you connect the 2 relations and make an estimation, for in pass 3 you connect 3 relations in join and make an estimation, and so on and so forth. And pass 4 onwards basically, so in this case we have to go up to pass 4 because we have 4 relations. So this is pass 1, this is pass 2, this is pass 3, and this is pass 4. So depending on the total number of joins in the relation, you might have to go to, let's say, pass n if there are n relations in the join query. So this actually I would say concludes the chapter 14 of query cost estimation and query optimization. And I would tell you to actually understand the cost estimation and query plan evaluation in a thorough detail, because you will be asked a large question on this in your exam, end term or quizzes. So it is important, there you will be given exact number of tuples in the query and other system catalog information, such as if join key is a primary key, or join key has an index on it, or selection predicate has a selection attribute has an index on it, so on and so forth. And based on that you will be asked to do the plan evaluation as well as cost estimation. The next couple of things that that we want to cover as a part of like general knowledge is that in nested subqueries basically are difficult to optimize. Remember, that is the reasons the IBM System R Optimizer has left out SQL queries which have nested subqueries in them from the optimization perspective. So we saw one such query couple of slides before. There is, by the way, typographical error which I will fix later. So this query actually can be evaluated in the most efficient manner if you just first evaluate the maximum rating by executing it only once, store it as a temporary value, and then use that temporary value in the outer query to evaluate the outer query. However, in the next query that which is also a nested query, you cannot make use of the previous kind of optimization that you did, because if you observe, the nested query is actually referring to each and every tuple of the outer query. So here I have been telling you that in the database management systems actually you can take a holistic overview of different computer science subjects that you have learned, and here you can see this actually is equivalent to in the programming languages concept using macros versus having to use pointers. So in the first query that we saw, where we are considering max rating of the sailor, this is like a hash define. that the hash define gets defined by the maximum rating from the table, and then you just use that in your query program. Whereas in the next query, since s.sid equal to r.sid and s has a reference to the outer query, this essentially means that the s.sid pointer keeps changing for each tuple, and you cannot really do a macro kind of evaluation of the inner query to execute the outer query by avoiding the inner query execution repeatedly. So these are some of the nitty-gritties, and nested queries anyways are a little less common in the SQL queries, so they have not been a focus of optimization. However, if you consider semi-structured data like graphs or XML, which also is stored in relational tables, and SQL queries are used to perform XML or graph queries, graph pattern queries on these semi-structured data, then they do have nested subqueries, and there oftentimes people come up with optimization techniques catered towards the semi-structured data and the nested subqueries of them. Other optimization approaches can be rule-based optimization, that you fix some rules with respect to which you follow, something like a decision tree in data mining. You can do randomized plan generation. So remember that the number of the plan exploration space can actually be very large, and oftentimes it can happen that if your size of the query is actually quite small, means that the total number of tuples that the query needs to access are very small, then the query cost estimation time can actually dominate the actual query execution time. So in that case, what you can do is that you can randomly generated a few plans and do the cost estimation only on them than doing exhaustive plan search. You can do parametric query optimization, multiple query optimization. So multiple query optimization considers that many queries that are getting executed simultaneously on the database server might have common subcomponents in them. By subcomponents I mean, let's actually consider this RSTU query, and let's say I have 50 queries running in, all of which actually have a join on R and T. So then what I observe is that instead of actually, so let's say that in this plan I am anyways doing R and T join together, but let's say in some other plan I was doing let's say RU join together, then that was joined with T, and then that was joined with S. So if I have this plan, if I am considering this particular plan for one single query out of the 50 queries, then I will have to do the evaluation of RU separately and then joining of R with T for this join separately. But if I consider, let's say, a plan like this, then I can observe that the join of RT has already been done for some other query. The results are cached in the memory, and I can directly use those results, whereby the cost of this entire query operator actually reduces to just estimate 3 rather than estimate 1 plus estimate 2 plus estimate 3. So there is a cost reduction over there. You can do view-based optimization, where view-based optimization is or even join table creation is similar to multiple query optimization. So let's say that I have identified that many queries have a join on R and T. So instead of performing the RT join again and again, I can create a view of RT join and store it as a base relation itself. Join table creation is again actually the same, I would say, synonym of view-based optimization, where you create a join of 2 or more tables and store it as a base relation, which is directly used if any query that you get in the future has the join on those tables. Selection conditions or projection conditions can be applied on top of this table directly by considering them as a base relation. So here we are ending the chapter 14 of query evaluation and cost estimation. I would again once again tell you to understand the query cost estimation properly, the way it is done methodically by creating left deep plan trees, doing single relation cost estimation, then in pass 2 combining the two relation, then in pass 3 combining three relations, etc. Because this makes the crux of the database system. Even if tomorrow you go for your job in a database company like IBM or Oracle, most likelier than not you will be encountering these query optimization or cost estimation at some point or other. So alright, so from next module onwards we are going to look at the database design techniques, normalization, etc. Thank you.